Let's begin with an introduction to neural networks. Neural networks form the bedrock of contemporary artificial intelligence. You'll discover how they are revolutionizing the approach to problem solving across various industries. So, what exactly is a neural network? It's essentially a computational model that draws inspiration from the structure and function of the human brain. Neural networks are designed to identify patterns and tackle intricate problems by learning from examples. The information is processed through interconnected nodes, also known as neurons, which are arranged in layers. Through training on data, the neural network refines and enhances its performance. Let's explore the biological inspiration behind neural networks. In biological neurons, signals are received through dendrites, processed within the cell body, and transmitted via axons to other neurons through synapses. Artificial neurons are designed to mimic this process. They receive weighted inputs, calculate a weighted sum, apply an activation function, and then pass the result to connected neurons. Now, let's understand the fundamental components. Neurons, also known as nodes, are the building blocks that process inputs and generate outputs. They incorporate activation functions and are arranged in layers. Connections, or weights, define the strength of the relationships between neurons. These weights are adjusted during the training process and are crucial for the network's learning ability. The output Y of a neuron is determined by applying an activation function f to the sum of weighted inputs W sub I, multiplied by X sub I, plus a bias term B. This can be represented as Y equals f of sigma W sub I X sub I plus B, where W sub I represents the weights, X sub I represents the inputs, B is the bias, and f is the activation function. Let's delve into the anatomy of an artificial neuron. An artificial neuron consists of weights and a bias. The neuron calculates a weighted sum of its inputs, adds the bias, and then applies an activation function to produce the final output. The fundamental equation of a neuron is output equals f of sigma W sub I X sub I plus B. Let's explore activation functions. Rectified linear unit, most commonly used activation function, is simple and efficient for deep networks. The function is defined as f of x equals maximum of 0 and x. Sigmoid is a classic activation function that maps values to a range between 0 and 1, commonly used in binary classification. The function is defined as f of x equals 1 divided by 1 plus e to the power of negative x. Hyperbolic tangent is similar to the sigmoid function, but maps values to a range between -1 and 1, making it suitable for hidden layers. The function is defined as f of x equals e to the power of 2 minus 1, divided by e to the power of 2 plus 1. Leaky rectified linear unit addresses the dying rectified linear unit problem by introducing a small negative slope when the input is negative. The function is defined as f of x equals the maximum of 0.01 times x, and x. Now let's discuss network architecture. The input layer receives raw data and distributes it to the first hidden layer without any processing. Hidden layers process information using weighted connections and activation functions. Multiple hidden layers enable deep learning. The output layer produces the final network predictions based on the processed information from the hidden layers. Let's explore the training process. The first step is forward propagation, where input data flows through the network, generating predictions through each layer. The second step is loss calculation, where the predictions are compared with the actual values to compute the error. The loss is calculated as the sum of the squares of the differences between the predicted and actual values. This is represented as loss equals sigma predicted minus actual squared. The third step is backpropagation, where gradients are calculated to determine how each weight contributed to the error. The fourth step is weight update, where weights are adjusted using gradients to minimize the error. The equation for weight update is W equals W minus alpha times partial loss, divided by partial W. Let's look at a simple example using an AND-gate neural network. Consider an AND-gate neuron with initialized weights W1 equals 1, W2 equals 1, and a bias of negative 1.5. To predict the output for inputs x1 and x2, a step activation function is used. The sum equals W1 times x1 plus W2 times x2 plus the bias. The function returns 1 if the sum is greater than 0, and 0 otherwise. Let's explore the applications and use cases of neural networks. Computer vision involves image recognition, object detection, facial recognition, and medical image analysis. Natural language processing includes text classification, translation, sentiment analysis, and chatbots. Time series analysis is used for stock prediction, weather forecasting, and demand prediction. Neural networks also play a crucial role in game AI, enabling game-playing agents, non-player character behavior, and strategic decision-making. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.